One type of function that we still haven't discussed is the exponential functions and how calculus is applied to them. So how do we work with limits, derivatives, and integrals with an exponential function? So let's recall what an exponential function looks like. It looks something like f of x is equal to b to the x power. And they can have two different shapes. They can drop as you move left to right, fall toward the x-axis but never touch the x-axis, or they can rise as you move from left to right, away from the x-axis going upward. And the thing that causes one or the other to occur is the base b. If b is between 0 and 1, like a fraction like 1/2 or 1/3, then you see the shape where the graph is falling. If the base b is greater than 1, then you have the shape of the graph going up as you move from left to right. And so you can see what some of the limits look like here. In the case of the falling graph, the limit as x goes to infinity of the function b of x is equal to 0, because it's approaching the x-axis where it would be equal to 0 as x goes to infinity. As x goes to negative infinity, that is, as x goes to the left instead of the right, the graph continues to go up and the limit would go off to infinity. If we flip it around and look at the exponential function going the other direction, then as x goes to infinity, you can see that the graph is going to infinity. As x goes to negative infinity, then the graph decreases and falls toward the x-axis, so it would be approaching to 0 as a result. So that's the basic behavior of exponential functions with limits. One end will point toward infinity, and one end will trail off toward 0. So we had this type of exponential function, the so-called natural exponential function, which is f of x equals e to the x, and this is an increasing continuous function. The domain is all real numbers, and the range is 0 to infinity. And so the limit as x goes to negative infinity of e to the x is equal to 0, like we see for it up above. As x goes to infinity e to the x, then that would equal to infinity. And the horizontal asymptote is the x-axis of the function f of x equals e to the x. And this is basically the same properties when any base is greater than 0. You'd have the same situation. So let's consider two limits, starting with the limit as x goes to negative infinity of 2 raised to the x power. So this particular function with a base 2 will have the graph that comes up this way and continues to rise. So in this case we are looking as x goes to negative infinity, so it's going off this direction. The graph of the function is going to get closer to 0. It's just going to get smaller and smaller, approaching to 0. So that would be what the limit is equal to. The limit as x approaches negative infinity of 2 to the x is equal to 0. Now we might see functions like the limit as x approaches infinity of 2 to the negative x minus 1. One of the best ways of getting a quick idea of what's going to happen here is to just look at the graph of the function. You can even use a graphing calculator to see it in a pinch. So I know this graph has to be shifted down and reflected due to the negative x and the negative 1. So it would originally go somewhere like this, but after reflecting it and moving it down, it's going to have a shape like this instead. And so as we go off to positive infinity, x goes to positive infinity, we can see that the graph is trailing off, getting closer to negative 1. So the limit is equal to negative 1. Now here's a limit where we have kind of two different functions at work. And so we have e raised to the negative x power, and we're taking the limit as x goes to negative infinity. So let's think of it like this. Let's think about this thing up in the exponent, the negative x to the second power. Let's let the letter u stand in for that negative x to the second power. Now as x goes to negative infinity, negative x squared would head off to negative infinity squared, or just negative infinity. And so what will happen here then is, thus u itself will go off to negative infinity as x goes to negative infinity. Since u is the same thing as x squared, and we see that x squared is going off to negative infinity itself. So how I'm going to rewrite my limit is I'm going to change this into the limit as u goes to negative infinity of e to the u. And from up above it tells us that that limit as x goes, or u in this case, goes to negative infinity, this is going to go off to 0. So that limit would be equal to 0. Here's sort of a similar situation. We have the limit as theta goes to negative pi over 2 from the right of e to the tangent x. Okay, so let's think about the tangent x for just a second. The tangent x had two vertical asymptotes, and it had one period of the graph going through between them like so. Negative pi over 2 would be the asymptote on the left. And we're saying as we approach that from the right, we want to know what the limit of the tangent is. Well, we see the graph falling downward toward negative infinity as we approach from the right. So what we're going to say here is let's let the letter u stand in for tangent theta. Then the u, being that that's taking the place of tangent theta, will go to negative infinity as theta goes toward negative pi over 2 from the right. So we'll write our limit now as the limit as u itself goes to negative infinity of e to the u. And again, it tells us at the beginning that this limit is equal to 0.